Let's do a problem where we search for the absolute extremes of a function of two variables over a triangular region. Remember in Calc 1, to find the absolute extremes of a function of one variable, you'd find the one and only derivative, first derivative of that function, and set it equal to 0, and determine your variable values that would make a derivative of 0. That would locate your critical points. And then if you had an interval of the x-axis that you were searching on, you'd have to test the endpoints of that interval too to find your absolute extremes. Here it's a little more complicated because we have a function that needs three axes. The region that we're looking at is in the xy plane, and then hovering over the xy plane up here in space is a surface, and we're trying to find the smallest and largest values that function or that surface takes on everywhere over this region down here in the xy plane. So we have to find critical points for this in the multivariable sense, which means we need to find the first derivative with respect to x, we need to find the first derivative with respect to y, and then we have to decide if there's a location where both of them happen to be 0 simultaneously. Now these derivatives are not too bad. Our function is right here. The first derivative with respect to x is y minus 1. The first derivative with respect to y is x minus 3. And so there's only one place where both of these would be 0. This one is 0 at x equals 3. This one is 0 at y equals 1. So they're both 0 at a single point, x equals 3, y equals 1. Now, let's double check that this point is even in this region. Let's go out 1, 2, so it's about, I'm guessing right about there. It is within the region. If this had turned out to be something like the point 6, 4, which would be out here and up here, it wouldn't be in the region and we wouldn't care about it anymore. But this one we have to track because this is one of the places where we might find our absolute extremes. The other places we might find the extremes are at the corners themselves or somewhere along each of the edges. In this context, where we're in a multivariable setting, what used to be checking the endpoints of an interval on the x-axis has now upgraded to checking along the boundaries of whatever region that we're interested in. So we have to take a look at these boundaries one at a time. The edges happen to be straight lines, so I'm just going to call these edges L1, L2, and L3. So there we found a critical point as a candidate for where our absolute extreme might be. Now we're going to look and find if there are any other candidates along one of the edges. So on this edge of our region, well, the equation of that edge is y equals 0, the horizontal straight line that is the x-axis. We go up to the function and we say, hey function, what do you look like if all we're considering for the moment is points where y is equal to 0? If we happen to be considering only points where y is 0, the function reduces to negative x. The derivative with respect to x there is negative 1. And it's never 0. So we haven't found any places along this boundary where in the Calc 1 sense we might find another critical point. So we didn't learn anything about that boundary. Or we learned that there's no points of interest on that boundary. On L2, this is the line otherwise known as x equals 0. We go to the function. We say, hey function, what do you look like if we're considering points for which x equals 0? and there the function reduces to negative 3y. The derivative of that is a derivative with respect to y, which is negative 3. This also is never 0. And so we have discovered no other Calc 1 type critical points on this function which happen to be hovering over either of these lines. Now let's take a look at L3. This is a line with slope negative 4/5 and a y-intercept of 0. Sorry, a y-intercept of 4. Duh. And so y equals negative 4/5 x plus 4 is the equation that describes this boundary of our region. We go to the function. We say, hey function, what do you look like if all we're doing is considering points for which this happens to be true? Well, this gets a little more complicated. We plug in this expression for y, like that. Now, there's a lot of algebra that follows up this as we tidy it up. So I'm going to speed it up a little bit. I'll assume you could go off onto the side and do this little cleanup by yourself. That shakes out to be negative 4/5 x squared plus 27/5 x, my hand will be out of the way in a minute, minus 12. And so now what we're going to do is take the derivative of that and look for critical points in the Calc 1 sense. However, I've run out of space, so pardon me while I open up a new page. Ta-da! So here's a fresh piece of paper. I've reconstructed our region that we're interested in. Remember, we have a function that's hovering in space over this region, and we're trying to find its absolute extremes, but only around the edges of or over this region itself. We don't care about anywhere else. We've discovered that there's a critical point of the function itself at the point 3,1, which is indeed within this region. We've looked along this edge of the boundary of this region and decided there were no other potential locations for absolute extremes because there were no Calc 1 type critical points over that boundary. We checked this boundary and found there were no potential Calc 1 type critical points there, meaning there's no more candidates for where our absolute extremes might be. And now we're in the process of examining L3. We found the equation of L3, plugged it into our function, and we've discovered that along L3, what was a function of x and y just reduces to this function of x alone. And now we're going to take the derivative of that function with respect to x. To get that. And that actually will give us a good old-fashioned Calc 1 type critical point at x equals 27/8. Now, the 27/8 is, what, a little bit bigger than 3? So right around here somewhere. So we make a little mark in anticipation of that. Let's go find out the y-coordinate that goes with that point. Now, here we have to go back to the representation of L3. L3 was the line negative 4/5 x plus 4. Here our x value is 27/8. That's a mess, and again, saving a little time. That shakes down to be 13/10, which is a little bit bigger than 1. This point that's already there has a y-coordinate of 1, so we go over here, we want something a little bit bigger than 1, and so we're talking about that point. That point has the coordinates 27/8 and 13/10. Good grief. That's just gross. But what we've done here is we've now categorized all the different places where our function could possibly have an absolute extreme over this region. So candidates for absolute extremes. Well, the function itself had a genuine multivariable critical point. That was the point 3,1. We exhaustively checked all three edges of the boundaries, and we came up with no extra possibilities, no extra possibilities. Oh, here's one. We came up with the fact that at 27/8, 13/10, oh, that's just gross, there is a Calc 1 type critical point hovering over this straight boundary, and that makes it a potential location of an absolute extreme. So we've found a critical point, a genuine critical point. We've checked our boundary and come up with that one extra point. And just like checking endpoints of intervals in Calc 1 when you're looking for extremes, we have to take into account the possibility that this function just happens to get as big as it's going to get or as small as it's going to get at one of the corner points itself. Not because they're critical points or anything, but just that's where we stop looking. So we have 5 candidates for where we might find the absolute extremes for this function. And at this point, it's number crunching, because we're just going to take each of these points, plug them back into the function, and find the biggest return and the smallest return. And those are our absolute extremes. So over here, I'll add a little extra column to my table. Remember that the function itself was xy minus x minus 3y. That was the function. So let's do this the easy way. Here, x is 5, y is 0. So 0, the first and third term becomes 0. This is negative 5 is the value of the function. At the point 0, 0, this whole function is just 0. At the point x equals 0, y equals 4, we would get 0, 0, negative 12. Like that. Let's skip this one. When x is 3 and y is 1, we would get 3 minus 3, so 0 minus 3 times 1. We would get negative 3. And then we need to plug in the coordinates of this point into that function. Anybody want to do that? No? All right, let's get help. So we're over here in Maple. In order to evaluate this function at the point x equals 27/8 and y equals 13/10. We could have done that by hand, but who wants to do that? It is worth popping open Maple or something else to get it done. So what I've done here is I've already used the little function defining gizmo from the left-hand expression palette in Maple to define my function f. It's a function of x and y, and the function is x times y minus x minus 3y. That's the one we're working with. There's 2 ways we can get the value of our function. We can do it like this. We can plug in 27/8 for x and 13/10 for y, just using the functional name negative 231/80. And just to get a intuitive sense of what that looks like, I've gone over here onto the left-hand side, which you can't see. It's outside the window I've cut for the video, but there's a little menu item that allows me to approximate this to 5 decimal places, and this is about negative 2 point, we'll just call it negative 2.9. The other way we could have done this is define x to be 27/8, define with colon equals y to be 13/10, and then just ask for f of x, y like that. That works too. And we're back. While we were in Maple, I borrowed the information from Maple and filled in this table. And so now I have the value of the function at the 5 candidate locations for our absolute extremes. And now we just dive in. We need to find the biggest value and the smallest value. Well, the smallest value is this one, negative 12. The function doesn't get to any lower value anywhere over our region, and so this is our absolute minimum. What's the largest value? 0. Everything else is a negative number. Like that. So there are the absolute extremes for this function over that region. Now, if this was a genuine homework attempt, having written out the problem statement, done all my work nice and neatly, I would write a concluding statement down here. Now, I don't really have a whole lot of space, but I'll at least start it. So there is an absolute max at the point, and let's see, that came from the origin. The x and y coordinates were 0, 0, and we should go in and put the value of the function as well. And an absolute min at, well, the x and y coordinates were 0 and 4, and the z coordinate was negative 12.